Princeton, and he's going to tell us about entanglement.
Great, thank you for the invitation, and thank you all for coming. So, I'm going to talk about entanglement entropy across a slightly deformed sphere. So here's the outline of my talk. I will start with a rather lengthy overview / introduction, where I explain my motivations to study this problem, and I will give the main results. So I think it will take like half of the talk, but if I manage to convey what excites me in this topic, then I think I will be satisfied with that. So then in the remaining time, I will discuss some technical details, how I obtain these results. So in particular, I will sketch how a perturbative approach to the calculation of entanglement entropy works. If we have time, probably we won't, then I will discuss how entanglement entropy evolves under RG. There's an interesting interplay, and finally I will conclude. So here's a lightning overview of Wilsonian renormalization as a motivation. So in my thinking, we will have a given microscopic description, which we know, and then as more common in condensed matter thinking, we want to know how the system behaves at long distances. So that's going to be in the IR. We want a long wavelength effective description. Now, if strong interactions are involved, this going between the UV and the IR involves some guesswork. So we base our thinking on symmetries or approximation schemes, but most of the times that's not enough, and we need to make some educated guesses. In the most familiar example, in QCD in 4 dimensions, in the UV we start with weakly interacting quarks and gluons, and in the IR we are left with interacting pions. So there, actually, this guesswork is replaced by the framework of broken symmetry, spontaneous breaking of chiral symmetry. So we can write the chiral effective Lagrangian and determine the interactions of the pions from just symmetry principles. But in a more generic situation, we need to make guesses, and so it's very valuable to have some generic insight into what constrains this guesswork. So one promising place to start is the intuition that RG leads to the loss of degrees of freedom. So how does this intuition come about? So in weak coupling, a field represents a degree of freedom at distant scales below the Compton wavelength. So just imagine a massive scalar field weakly interacting with some other degrees of freedom. So below its Compton wavelength, it's really dynamical and you see it interacting. But at longer distances, its effects only manifest themselves in renormalizations of couplings. So you can integrate this field out, and you are left with the other degrees of freedom, which are not massive at this energy scale. So by this, we reduced the number of degrees of freedom. So going from the UV to IR, we lost some degrees of freedom. And the question is, so this was weak coupling intuition, the question is whether we can formalize this intuition.
The chiral symmetry breaking energy scale is higher than the energy scale of confinement.
Chiral, I mean, it's approximately the same scale, right? People usually code the chiral symmetry breaking temperature to be around like
in the real QCD, they are separate scales.
Yes. So I mean, so if we neglect quark masses, then in the IR we just have massless pions. So no matter what my strong dynamics did, the important thing that determines the dynamics of Boson bosons is chiral symmetry breaking. Confinement doesn't really matter.
What I was worrying about is that in the holographic setup, sometimes you could have confinement temperature which is higher than the chiral symmetry breaking temperature. In that case, maybe
yes,
the last scale should be the confinement.
Okay. Yes, I'm going to be working at 0 temperature most of the times because I will need exact Lorentz symmetry for what I'm going to say. So if we look at QCD at 0 temperature, then I think what I said is correct. Okay. Thanks for it. Okay, so this is just some motivation why we want to have some understanding of how to define degrees of freedom in RG. And so one of my thesis sentences is that understanding entanglement entropy in QFT leads to an improved picture of RG. So how does this come about? So we take our field theory to live in flat space. So this is just a spatial slice at constant time. We divide it into geometric regions V and its complement V bar. And the boundary of V I will denote by sigma, and I will call it the entangling surface. So entanglement entropy is defined as follows. In a local theory, there are degrees of freedom living inside V, and there are degrees of freedom living inside V bar. And the Hilbert space factorizes into tensor products, degrees of freedom supported on V, and degrees of freedom supported on V bar. So that's my first equation here. Of course, there are subtleties in gauge theories, but let me not go there. So I'm just thinking about the lattice regularization of my theory, and then everything is well defined. Okay, so I will denote my vacuum state with 0. And the reduced density matrix is defined by a partial trace over the vacuum projector. So I trace out degrees of freedom in V bar. So that defines the reduced density matrix. The meaning of it is that if I restrict my experiments inside V, and I throw away information in V bar, if I know this density matrix, I can determine all the correlators which are supported in V. So this is very similar to the familiar setup when I have an environment and I have my system of interest, and I can trace out the environment, and that will give me a density matrix for my system. And if my environment is a Heath path, but then I will just get a canonical density matrix for my system. So this is, but in this case, I don't have an independent Heath path. I just trace out the rest of my QFT vacuum state. Okay, so if we have this reduced density matrix, then we can define an entropy associated to it, just the usual von Neumann entropy. So that's what we call entanglement entropy of this geometric region V. So it depends on the region. Okay. If we are in a CFT, then there are only two scales that we can play with. There is the characteristic size of this geometric region V, and then there's the cutoff, and then entropy is a dimensionless quantity. So in a CFT, we can determine how this entropy depends on these quantities. Yes?
I was just wondering, is it ever useful to think about this picture in empty space rather than in position space?
There are a handful of papers written about it. So, for example, in a free theory, the vacuum wave function is a product over different momenta. So by this you could maybe characterize whether your theory is interacting or not, because as you switch on interactions, you will have mixing between different momenta. So it might be useful for this purpose, but people haven't made much progress. Thanks.
In 2 dimensions, there are no separating term.
In 2 dimensions, so there are. I didn't exhibit terms that go to 0 as you take the cutoff to 0. So there is a constant, but this constant cannot be given independent meaning, because if you redefine your cutoff, or you scale delta to be to do something like this. So you just rescale your cutoff, then your log r over delta will go to log r over delta minus log lambda. So you can just eat up constant term. Yes, good question. Yes.
Also, I'm wondering for path integral representation, is it like choosing a basis where some functions have support only on V and others only on V bar?
Yes, I will discuss the path integral representation of this calculation, and then it will become clear. Yes. Okay, so what I wanted to show you here is the first thing that people learned about entanglement entropy is that its leading divergence, as you take the cutoff to 0, so this delta is a space, it's not a momentum space cutoff, it's a short distance cutoff, is the famous area law, where by area we mean the area of the of this entangling surface. So for example, in the 2 + 1 dimensional setup I exhibit here, it would be the length of the boundary. So it has to, so we are, in that case we are in 3 dimensions, and it has to be divided by delta to make it dimensionless. So that's the first statement, that the leading divergence is like that. And if you use the property that the entanglement entropy of V and the entanglement entropy of V bar have to be equal in a pure state, then you can conclude that you can only have only in the odd dimensions you can only have odd powers of the cutoff. In even dimensions you can only have even powers of the cutoff, and in even dimensions you also have logarithmic terms which are related to trace anomalies. So in the CFT, in 2, 3, and 4 dimensions, these are this is the structure of entanglement entropy. In particular, in 2 dimensions, the overall coefficient is just the Virasoro central charge divided by 3. But that's just normalization. Okay, if we have other scales, then this structure becomes a mess. But with Hong Liu, my thesis advisor, we made a proposal. I think we argued convincingly that if you take the following differential operators to act on entanglement entropy, so R is just the characteristic size, so derivative with respect to R means that you're comparing 2 regions which have the same shape, but you blow them up a little bit. So in 2 dimensions, you just take the logarithmic derivative with respect to R. In 3 dimensions, you do something more complicated.
So this formula only applies to the gapless system.
This one is only applies in CFTs.
Gapless or with gap.
CFT means
Yeah.
It's gapless, and on top of being gapless, there are no other scales. Because you could have a gapless system, but you could have some massive excitation. Yes. So the statement is that if I have a renormalization group flow from a UV CFT to an IR CFT, then these quantities will be finite. So as you can then, if you take these derivatives, then you can take the cutoff to 0, and you won't encounter any divergences. So for example, in 2 dimensions, we're taking the logarithmic derivative with respect to r. So in this case, that would just strip this log, and we will be left in a CFT with the central charge. And this is also designed in 3 dimensions to get rid of the area log piece and extract. In a CFT, it would just pick out this guy in an RG flow. That piece would have an R dependence, and it would pick out something. But you can think of these proposals as capturing entanglement per scale, where R is a proxy for RG scale. Okay, so this is some statement that if you think about it a little bit, you can argue for based on just general RG picture. So this could help you in defining entanglement entropy in the true continuum limit, because for this definition you have to keep your cutoff. Okay?
Sorry, you're still assuming Lorentz invariance along the flow.
Yes.
Everyone.
I assume Lorentz invariance along the flow, but these quantities actually, even at finite temperature and chemical potential, would, because basically if in an intrinsically Lorentz invariant system you turn on temperature, it can be thought of as some deformation of the theory. And the divergences are intrinsic, divergences are the same in the vacuum state and in an excited state. Just like if you're doing thermal field theory, you can use the same counter terms in your renormalization as you can in your vacuum. So, divergences don't change by exciting your state. So these things can be argued to be UV finite even at high temperature. Okay, so yeah, let me go back to here, and so you will have to remember that these guys are the universal pieces that we are after. And so in 2 dimensions we saw that it's just a constant, the Virasoro central charge. In 4 dimensions, it depends on the shape of the entangling surface. Of course, in 2 dimensions, the entangling surface is just 2 points because it's the end of an interval. But here, it's a 2-dimensional manifold, and from the trace anomaly, one can derive this formula which determines the shape dependence of this universal piece. So it has 2 terms. One is a topological term. It's just the Euler density on this 2-dimensional surface. So it will just give you the genus of the surface. It's multiplied by the A times central charge in 4 dimensions. And then there is another guy, which is an integral of a particular combination of the extrinsic curvatures. Okay? So this expression is Weil invariant, and that's how it was derived. So is this clear to everybody? This is a local integral on my entangling surface, which is a 2-dimensional surface. Okay? If you look at the form of I2, then you can immediately see that it's positive semi-definite. And so you can see that for genus 0 surfaces, genus 0 entangling surfaces, this expression is minimized by the 2 sphere.
Sorry, what's the difference between k squared and KABK?
Oh, sorry. K squared, so K is the extrinsic curvature, and K squared, by K squared I mean the square of the trace of K.
Ah, okay.
So it's a different index contraction. Okay, sorry for not explaining that. So in 4 dimensions and in higher even dimensions, because this universal piece is related to a trace anomaly, it's expected to be given by an integral of some local density of geometric quantities of the entangling surface. But in odd dimensions, there is no trace anomaly, and correspondingly, so let me show you again that in this three-dimensional example, the universal piece of entanglement entropy is just a constant. It's not multiplied by a lot, and it's expected to be a non-local expression. So, of course, determining non-local expressions is a lot harder, and not much is known about it. So that was one of my motivations to study this problem, and I studied it in a perturbative framework. So let me define my Antagonic surface in polar coordinates by the following expression. It's approximately a sphere. So there's the one, and then there's epsilon plus a spherical harmonic expansion of the Antagonic region. So here's a three-dimensional example, 2 plus 1-dimensional example of putting a wiggle on the circle. Okay, so epsilon, if you can see, is the amplitude of this wiggle. Okay, so this is just Y's are form a complete basis, so I can do this. This is the most general deformation of the sphere. So I will discuss why I start with a sphere. But we know a lot about spheres in conformal theories, but we don't know anything about waveforms. So then one can use perturbation theory in epsilon, and the first result I obtained with Andrade is that among all shapes parameterized by these A's, which are the relative weights of spherical harmonics. So among all shapes, the sphere is a local extremum of the universal piece of entanglement entropy. What this means is that I take an epsilon expansion of this universal piece, and the linear in epsilon piece vanishes. So then it's a local extremum. And then, so there's the sphere value here, and then there's an epsilon squared piece, which is multiplied by some shape-dependent coefficient. So from ADS CFT, as I will discuss, I determined this shape dependence coefficient recently, and I got the following result. So two things are worthy to note. So first of all, it's just the sum over of the contributions of different spherical harmonics. So different spherical harmonics at this order don't talk to each other. At higher orders in epsilon, they would. Then there's some polynomial of L, where L is just the angular quantum number of the spherical harmonic. And the overall coefficient is CT, the stress tensor, the coefficient of the stress tensor 2-point function in the CFT. So that was kind of unexpected, that in every CFT it has a universal, the shape dependence has a universal form, it's just multiplied by the stress tensor 2-point. And then there's a coefficient which is just dimension dependent, it involves some gamma functions that I didn't want to pollute my slide with. Okay, so any question on this? Okay, so let's see some examples to make it maybe more digestible. So in 3 dimensions, I just have the angle of phi, so my spherical harmonic decomposition is just becomes the normal Fourier series. I use real spherical harmonics because my surface is real, but that's just for convenience. And so the result is downstairs. Sines and cosines contribute by the same amount. That's not surprising because they are related to each other by rotation invariance. And then this shape dependence is just L cubed minus L. Okay? And then there's CT and some numerical factor. Yes?
So what if I turn off all my A's except for 8 pi?
Okay.
Then my F3 will vanish, right?
And the reason for that is that you just describe a slightly shifted surface, a slightly translated surface in polar coordinates.
So it's still a perfect circle.
Yes, it's still to this order, it's still a perfect circle. And so L equals to 0 is just blowing up your disk in this case, but because we are in a CFT and things only depend on the shape, not the size, you again get 0. Yes, very good. Okay, in 4 dimensions, we know the exact formula as I showed you, so it was here. So if I do this epsilon expansion for this formula, I get the following, and because I know, so I get C4, but C4 is exactly related to CT in a 4-dimensional conformal field theory. If you go through the numerical factors, then you get exactly the result I obtained from holography, so that gives us more confidence in that result. You can do the same exercise in 6D. I won't do it for you here, but you get again something that is known from field theory. So I have 2 remarks. One, and you already got that L equals to 0 and L equals to L equals to 1 don't give contributions for the reasons I explained. And from the power of the largest power of L, you can read off whether your formula comes from has a potential of coming from a local expression or not, because from the property that V and V bar have the same entanglement entropy, you can deduce that if this universe of these comes from a local expression, it has to involve even powers of the extrinsic curvature. That will give you even powers of L. So in 4 dimensions, as you can see, the largest power is L to the 4, whereas in 3 dimensions, it's L cubed. So in 4 dimensions, as we saw, it comes from a local expression, but in 3 and 5 and higher odd dimensions, by this result, you can rule out that it comes from a local expression. Because you just cannot write down an even polynomial in extrinsic curvatures and derivatives that would give you such a result. Okay, so that's already a valuable insight. Okay, so how is this all related to the number of degrees of freedom? So we saw that in 2 dimensions, the Virasoro central charge appears, and famously, due to the work of Zamolodchikov, we know that that obeys the monotonicity theorem. So you could say that, okay, C counts the number of degrees of freedom of my 2-dimensional theory, and because it decreases under RG flow, we managed to formalize the intuition that degrees of freedom have to decrease under RG flow. Similarly, A4 and C4, so the 4-dimensional trace anomaly coefficients, appear in entanglement entropy. And A4 was conjectured by Cardy to decrease under RG flow, and recently Komargotsky and Schwimmer actually proved that result. So again, we see a relation between decrease of number of degrees of freedom and entanglement entropy. And this relation is made even stronger by the work of Cassini, Huerta, and Myers, who showed that that one can relate this entanglement entropy across the spherical region to the free energy on a sphere. By free energy, I just mean the following thing. You take the Euclidean sphere partition function and take the negative logarithm of it. So that's a result in CFT, and that's why I said that we will start our exploration from spherical entanglement regions, because there we know this result, and we can calculate partition functions rather effectively, whereas we don't have very effective methods for entanglement entropy. Excuse me.
But why does the central charge, I mean, it's not really proportional to the degrees of freedom. I mean, you could have negative central charge as well.
In a unitary theory, these
Okay,
things are.
okay.
Yes. So actually, entanglement entropy is only defined for unitary theories. It's a Lorentzian concept, and it doesn't make much sense in non-unitary theories. For example, your reduced density matrix has to have unit trace, and that is not preserved in non-unitary theories. Or maybe in some non-unitary theories it is preserved, but not. Under no-unitary time evolution, that's usually not preserved.
But you can still have different degrees of freedom contribute differently to the central charge. I mean,
Yes.
different amounts.
Yeah, so it's not the usual count in many cases. So for example, it's not like, oh, a gauge field will contribute 2 because it has 2 polarizations, a scalar field with 1 because it has 1 polarization, Fermions similarly. It's not this naive count. But if you have n scalar fields which are weakly interacting, this measure will give you n times that of a free scalar field. Similarly with fermions and vectors. And you can, and so Cardi proposed these decreases of number of degrees of freedom by studying known examples, for example QCD, that indeed if you start from the UV and then you go in the IR, count Goldstone bosons, that this A always decreases. So, I mean, this is not the only definition that you could give for the number of degrees of freedom, but it's a useful one. It decreases for any RG flow, so we will go with this. This will constrain every RG flow, so this is a useful tool. Okay? So, again, there's a relation between free energies and entanglement entropy, and it's maybe more believable that if the free energy is big, then you have lots of degrees of freedom. If it's small, then you have less. So that maybe gives a better intuition why entanglement entropy of a sphere should be related to the number of degrees of freedom. And so the history here is that that this sphere free energy was conjectured to decrease under RG flow by the following Princeton people, Jeffrey Skabanov, Kufu, and Safdie, and then in parallel development, Myers and Sinha conjectured that entanglement entropy decreases. And then this paper showed that these two conjectures are the same. Okay? But these are just definitions at the fixed points, at the CFTs, and what do you do in between? So that's why we started working on it, and so our proposed way of extracting this entanglement per scale, so by acting with differential operators on the entanglement entropy, can be shown to be monotonic in 2 and 3 dimensions. Unfortunately, in 4 it doesn't work, so it's not the final word on the story. But so what we did, we just studied it in lots of holographic and free theory examples, but then we just made the proposal that it's true, and a couple of weeks later, Cassini and Huerta actually proved it. So now we have these RG monotonicity theorems in 2, through Samoshikov, 3, through this work of Cassini and Huerta, and 4, through the work of Markovsky and Schwimmer. So we have monotonicity results, which are true for any Lorentz invariant RG flow. And so one thing that didn't satisfy me for a long time is why, from the entanglement entropy perspective, why did we need the sphere? Why didn't we start from an ellipse or some other funny shape? And the tentative answer that I can give now is that, first of all, the sphere minimizes entanglement entropy among all shapes, because this epsilon squared piece that I had here, so this epsilon squared piece is positive for all shape deformations, and it's because CT is positive. for any unitary theory. On the other hand, it's known that CT doesn't obey monotonicity results. So there are theories where CT decreases, there are theories where CT increases. So from this, one can conclude that no other shape obeys monotonicity results. So actually,
Sorry, but this argument, does it work for the plane? I mean, the infinite strip, is it? You
No,
wouldn't be able to use this argument for the infinite strip.
so in the strip case, I mean, yeah, it doesn't work because we were looking at shapes which are close to the
Right.
sphere.
So
and
how does that? Okay, so that's a.
yes, okay, but in 4 dimensions, I know that the infinite strip has entanglement entropy proportional to C4, and C4 is known to not decrease under RG flow. There are theories where it increases, there are theories where it decreases.
But I thought that non-energy condition would tell you that you can define the C function appropriately. So
In Einstein gravity.
Yeah.
But
from Meyer's paper, I suppose.
So Meyer-Sinha actually showed that the only thing that obeys the C theorem, I mean, not every theory with a holographic dual will have A4 and C4 very close to each other. So you cannot find holographic duals. I don't know of examples of holographic duals where C4 increases under RG, but there are field theory examples, supersymmetric QCD examples where it happens. So actually, there's a paper by Dan Friedman and collaborators where they prove that it's really not possible to take A4 and any combination of A4 and C4. There are theories that will violate the monotonicity of this quantity for any of.
I was just wondering about your statement about monotonicity for the. So I thought, for the infinite strip, there's some holographic way to guarantee monotonic flow for assuming no energy.
Okay,
So-
but that means that these holographic RG flows don't capture all the field theory possibilities. It's
Okay.
probably true that for theories for which you have weakly curved holographic duals, other more stronger statements are true. These are field theory statements that are. So my philosophy for using ADS-CFT will be just to learn stuff and then try to do field theory calculations to prove stuff. Okay? So this leads to an improved understanding of RG. We start from UV fixed points, then we flow to IR fixed points in the space of couplings G1, G2. But now we elevate this whole thing into a landscape. We add an extra dimension that would be this universal part of entanglement entropy. And the rule of the game is that the RG brings you down on this landscape. Okay, so this leads to a fundamental constraint on the gases that you can make. Your condensed matter friend makes a gas, starting with a system and then flowing in the IR, and he writes down the theory for you. Then you calculate this F in the UV and IR, and you can tell him whether his gas passes this check or whether it's ruled out. So you can really use this. I mean, the applications are in their infancy, but yeah, maybe let me just say one example. So let's take 3-dimensional quantum electrodynamics with NF fermions, and then you can conclude from running this argument and running into a contradiction that for NF, so you assume that this theory will confine. And then you run this argument and you count Goldstone bosons in the IR, and you can conclude that for NF greater than 12 fermions, this theory cannot confine because it would violate this inequality. Because I'm running out of time, let me not discuss it unless there are questions about this point.
Just a quick, so is that like in contradiction from what you naively guess? Like,
mean, for beta function in this case, because the gauge coupling is dimensional, mean you just see that it goes to strong coupling, and so then you don't know much. So it's not like in 4 dimensions. Like you can run this argument in 4 dimensions, but there you would get a very poor estimate, like something NF of order 500. So QCD with 500 fermions would not confine, but you know that the actual number is like, I think 33 over 2 or something. Of course, you cannot have fractional numbers. Okay, so let me go back to your question about how you do a path integral representation of these calculations. So, how do you write a path integral for the reduced density matrix? So first, let me take just the vacuum projector and write the path integral for that. Actually, for the matrix elements of that. So phi minus and phi plus are field eigenstates at t equals to 0. And so I just need basically this. So phi minus, and rho stands for just 0, 0, the vacuum projector, phi plus. So I can easily write a path integral for such an amplitude. It would be just a transition between the vacuum and the state phi plus and phi minus. So that's just the path integral on the upper half plane with boundary conditions phi plus, and on the lower half plane Euclidean path integral with phi minus. So that's just the usual representation of the wave function in terms of Euclidean path integral. Is that familiar to everybody? Okay, so as you can see on the right hand side, I put boundary conditions on the upper half side of the x-axis to be phi plus, and the lower half to be phi minus, and then I do the Euclidean path integral on the rest. So that's just this vacuum projector, the matrix element of this vacuum projector. So of course I could separate these two things because there's no talking between the upper and lower half plane at this moment. So then the next step is to partially trace. And to partially trace, you erase some of this line and this line and integrate over, so that's going to be V bar, and so you integrate over those degrees of freedom. What I mean by that is that you identify phi plus and phi minus on these complements, and so that would correspond to sandwiching the density matrix with a complete set of states on that Hilbert space, and then integrating over them. So this is the path integral for the matrix element of the reduced density matrix. Is that clear?
Wait, so where is V bar?
V bar is here. It's at t equals to 0. And I chose the complete set of states on V bar to be these field eigenstates. And I just integrated over them. That corresponds to partial tracing. Okay, so this is not my work. This is standard knowledge in this part of the field where people calculate entanglement entropy. But now the problem is that you will have to calculate rho log rho, and that doesn't have a path integral representation. Instead, you do the following trick called the replica trick. You define the Rayleigh entropy, which will be just log, again, this overall factor doesn't matter that much. It's trace rho to the q, where q is an integer. Okay, so we want to calculate this, and I will let you know right away why. But this one has a path integral representation that you can see on the right hand side. So why is that? Because we take Q density matrices and we multiply them together, so that if you think of the density matrices as real matrices, you are contracting indices pair by pair. So what happens is that you start from this first density matrix. This was its second index. You contract that with the first index of the next density matrix. So you are doing something like trace rho to the q is equal to rho. This is the first copy of the theory, ij. Then comes the second guy, ja, and so on. And here I'm calculating trace rho to the q. So as I said, the index contraction of J corresponds to identifying the field value on the lower side of the cut with the upper side of the cut on the next sheet. This is the path integral representation of Z3. And then in the end, you have to contract the upper side of this cut, the last cut, with the lower side of the last cut to take the trace. That's just the cyclicity of trace. Okay, so we calculate this guy. We divide by z1 to the q, which is just the normal partition function raised to the qth power, take the log, take this thing. So why are we doing this trick? Because if we take the q goes to 1 limit, which is tricky because this range entropy is only defined for integer q. So if we take that, then we get entanglement entropy. So if you expand this expression around q equals 1, then the first term vanishes from the normalization of the density matrix. You just have log trace of rho, which is log of 1, which vanishes. And so you have to go to second order, and there you get the entanglement entropy, and these q minus 1s vanish. Cancel. Is that clear how you get in the q goes to 1 limit this guy, the entanglement entropy? Okay, so this is a very cumbersome way of getting entanglement entropy in QFT. You would have to calculate the partition function in this n-fold copy, and then you will, even if you can do that, the analytic continuation will be the nightmare, and this has only been done in very simple setups. Okay. So ADS-CFT comes to the rescue. I included this in the list because there was a long-standing conjecture by Ryut and Takanayahi for what the correct formula in ADS-CFT is, but recently it has been proven by Lefkowitz, Maradasena, and also for higher curvature gravity theories by Shidong. And it turns out that you just do the same cumbersome calculation in ADS-CFT, but everything simplifies in the q goes to 1 limit. So their proposal is that you take, so in ADS-CFT you have a field theory living on the boundary of a one higher dimensional ball. And so in this picture, these 2 points are representing my entangling surface. And you hang down a minimal surface and anchored on this boundary entangling region. And the statement is that the area of this surface, minimal area surface, divided by 4g Newton, just gives you the field theory entanglement entropy. Of course, this is a leading in order in n statement. And this formula is tantalizingly similar to the Bekenstein-Hawking entropy formula, except that the meaning of A is different. A is now not an area of a black hole horizon, instead it's an area of a minimal surface. But there must be some relation. And you know, you can think of black hole entropy intuitively as entanglement entropy because you are an outside observer, you forget everything that happens inside the black hole that results in a mixed density matrix.
And she don't compute the entropy from safety side?
No.
I know Hartmann and Faulkner they did,
Yes.
and they found a match.
Yes.
But in the hypothetical case, I don't know how to prove.
So there was the conjecture of Ryu and Takanayaki, that's fine. Then Hartmann and Faulkner calculated in CFT side everything in two-dimensional CFT, and because there in two-dimensional CFT you can evaluate partition functions on these complicated genus, higher genus surfaces. And then they calculated in ADS CFT by some complicated evaluation of the gravitational action on some Handel-Bundy geometries. Yes, so there they explicitly calculated everything and everything matched. So that can be thought of as a proof. And then Lefkowitz and Maldacena did this replica method in any dimensional gravity, and they managed to analytically continue the Ornstein gravitational action to Q goes to 1. So they don't have the geometries dual to non-integer Q, but they know the action, how to analytically continue the action from integer values of Q to Q goes to 1. And what they got is that it's exactly equal to the minimal surface area. And that what Shidong did is that he generalized the Lefkowitz-Maldacena thing which worked for Einstein gravity to higher curvature gravity.
Is there evidence from the safety side for the higher derivative case?
I mean, for example, okay, that's a good question. So in the case of 4 dimensions, as I showed you in the introduction, there is this known formula by Solovykin for the universal piece in entanglement entropy in 4 dimensions. And for example, my calculation shows that indeed the coefficient, which was C4 in front of that term, is holographically the same thing. I'm working in higher curvature gravity, so that's a test. I think there are papers by Myers where, for specific cases, it reproduces that formula, but it hasn't been tested extensively. That I give to you. Okay, running out of time. Let me see what. Okay, so I think I will skip this because I don't have time. So these slides are just discussing how you can actually obtain an operator expression of the reduced density matrix for special geometries, half space and sphere in CFTs. It's one thing that is interesting is that they are just local integrals of the energy, the 0,0 component of the energy momentum tensor, weighted by some things. Okay, but I have to skip this. So, but we know an explicit expression for the reduced density matrix, and then you can imagine that you can perturb around it. You introduce some deformation of the metric, and that corresponds to shape deformation. So using all this formalism with Andrealis, we showed that the linear term in epsilon, if you remember, that vanishes for spheres. And then to go to second order, nobody knows how to do that in this field theory computation. It's just technically too hard. So what I set out to do is to calculate the second order correction in gravity and to distinguish between different central charges. So one hallmark of ADS CFT is that unfortunately in the Einstein limit you cannot distinguish between many central charges because you just have one coupling constant, the Newton constant, so everything is just equal. A4, C4 are equal to each other and they are equal to CT, and it's just not powerful enough to distinguish, but as we discussed, Shidong has a formula for higher curvature gravity. Of course, higher curvature gravity is not a very healthy theory, but here I'm just using it in the kinematical sense So I just use it to say that a higher curvature gravity theory is expected to give me all the possible conformal structures in stress tensor endpoint functions. So I just use it to parameterize possible dual theories which have different stress tensor endpoint functions. Because in the gravity side, I have new gravity vertices introduced by these higher curvature couplings. I'm not saying I can parameterize every CFT by this, but at least I can activate all conformal structures. So the coefficient in front of them might not be equal to what you get in a real CFT, but at least I can distinguish between all central charges and all higher point functions if I want, and if I'm powerful enough. So in this setting, I'm working on into linear ordering higher curvature couplings so that all the insanity of higher curvature gravity theories doesn't spoil me. I managed to show that in any higher curvature gravity theory, I always get CT in front of this shape-dependent expression. And in the lack of time, I cannot explain everything, but it was really remarkable for me because I first thought this formula of Shidong consists of walled entropy in these coordinates, and this is just the walled entropy. And then there is another term which is an integral of the extrinsic curvatures of this minimal surface. And I thought there's no way that these two terms would give the same angular dependence. And they give different, they result in different integrands, but so they, for example, correct the area law in different ways, but somehow for universal pieces, I don't understand every detail of it, but just by direct calculation, I get that they give contributions that are proportional to each other, and on top of that, the coefficient always combines to become CT. So for every higher curvature derivative, higher derivative theory, you would get a different expression for CT in terms of the higher curvature couplings. But somehow they combine into CT for every theory. And by every, I really mean every. So there's a formalism in which I can treat everything at the same time. So because I get CT for every holographic example, and as I told you, the stress tensor endpoint functions are parameterized by these, and from field theory I expect geometric reformations to be captured by stress tensor endpoint functions, I think it's reasonable to assume that this formula, although I obtained it from ADS-CFT, is valid in all CFTs. And we saw in 4 and 6 dimensions that where the results are available, it's indeed CT which appears here. So this conjecture is more contentful for all dimensions. So of course it would be nice to prove it from field theory, but we don't have the tools yet. Okay, so as I anticipated, I have to skip this whole RG evolution of entanglement entropy, but you got the punchline, it decreases, at least in 2 and 3 dimensions, and also in 4 dimensions, between the fixed points it decreases, but it's this universal piece that are cumbersome differential operator acting on entanglement entropy procedure extracts that one is not monotonic, so there's clearly space for improvement. So let me conclude. So I can conjecture that in a CFT, among all shapes topologically equivalent to a sphere, the sphere minimizes entanglement, the universal term in entanglement entropy. So I back this conjecture up by obtaining an explicit formula for the shape dependence and seeing that the sphere is a local minimum. Of course, to prove it globally, probably one would need new methods. And I was able to answer the question why we look at spheres when we want to define the number of degrees of freedom. The answer is that any deformed sphere won't obey monotonicity results. And so the main punchline is that entanglement entropy is a sensitive probe of RG flows, and one can learn some information which one can use in model, even in model building, about strongly coupled theories, which I think is remarkable. So thank you for your attention.
Any other questions from Mike?
Yes. Do you know what happens if you have a different topology in the sphere?
I mean, in 4 dimensions, I do. So I could have done this more optimally. Okay, so in 4 dimensions, I do. There's this explicit expression which is valid even away from genus 0. So this guy would just give you the genus of your surface, because it's just the integral of either. So there is a paper by Gibbons and collaborators where they prove that in 4 dimensions the sphere is a global minimum even if you change topology. That paper is wrong, by the way. So there's unpublished work of Eric Permuter where he shows that that's not true. So these people assume that A and C are equal to do their proof.
So looking calculation is for the free safety, right?
No.
No, for general safety.
Yes. I mean, to say it's a calculation, I think it's an overstatement. He uses these. So we had these replicated geometries, and he uses some method called squashed cones, which continues these geometries to non-integer cube. I myself personally, I don't understand every detail of it, but somehow he obtains this formula. So and he obtains it from the conformal anomaly, the trace anomaly, which is true for any CFT. And this formula passes checks, so it might be just my misunderstanding or me not understanding his proof completely. I think it's, even if not every step is well justified in his derivation, the formula is believed to be true in every setting. Every test of it gave good results. So, but it's very non-straightforward, because in 4 dimensions he hasn't been able to do the same, or in 6 dimensions, I don't know what I said. In 6 dimensions, the same procedure hasn't been done, whereas you would think that if this is just a calculation, the geometry is available, people who understand it should be able to get it, but they haven't been able to do so. I myself am not an expert.
So you were saying that the proof that the sphere is a global minimum is wrong, but is also the result wrong, or is it still believed to be true?
No, I think the result is not true. So I think Eric Permuter has geometries which are not topology, which are higher genus, and they go below the sphere.
But that's in different dimension, or?
It's 4 dimensions. I mean, the other is 2 this expression, right? It's something like 2 minus 2g, so it goes negative. Yes, I was also confused by that. Yeah, this term goes negative.
Okay, if there are no more questions, let's mark again.